Hello again, physics friends. Today we are focused on energy and work, and this discussion is really the start of a journey for the rest of this class where energy is going to play a key role. And we are going to talk about Lagrangian mechanics, which is founded on quantities of units of energy, scalar quantities, specifically on kinetic energy and potential energy. So we want to today make sure that we have a firm foundation on energy, and we'll do a quick example that we've actually seen before, looking at how to solve mass on a spring using energy arguments and the Lagrangian as a reminder of some of the definitions that we'll be using for the rest of the term. So let's think about the following scenario. So we have a mass on a spring, and we'll have an equilibrium point for that spring, which will indicate here. And then we'll look at our x-coordinate, which will be a deviation from that equilibrium. And of course, we need a spring itself with a spring force, a spring stiffness K, and we'll have a mass of the block M. Now, there's a force exerted by the spring, and that force I'll label FSP. That force tries to bring the mass back to its equilibrium, and that spring force is given by minus kx. So we have, using Newton's second law, we have the acceleration of the box, 1 over m times the net force on the box. And in the x direction, there's only one horizontal force. That force is minus kx. The acceleration in the x direction can be written as x double dot. And so we find ourselves in the situation where we have a differential equation, an equation of motion for the system that tells us that the acceleration of the system is proportional to the displacement, and the proportionality constant depends on the stiffness of the spring, the mass, and there's a minus sign. In other words, the key idea here is that the acceleration of the system is proportional to minus x. The more the displacement, the more the acceleration. Okay. We've done a similar thing before, but I also want to solve this problem using the Lagrangian. And in the Lagrangian, we have the fact that we have this quantity called the Lagrangian defined to be the kinetic minus the potential energy. And notice here that we're going to use T for the kinetic energy and U for the potential. Okay. And there's going to be an expression that relates the Lagrangian and the derivatives of the Lagrangian, and that is that if you take partials of the Lagrangian with respect to the velocity element, the time derivative of that is going to equal the partial of the Lagrangian with respect to the coordinates. And that ends up also going to give us the equations of motion. This is all energy-based. There's no talk of forces. There's no talk of vectors, and so on. So we can play this out. The kinetic energy here is the kinetic energy of the box, which is m over 2 x dot squared. The potential energy is that of the spring, which is k over 2 times the stretch squared. And therefore the Lagrangian is the difference of those two, m over 2 x dot squared minus k over 2 x squared. So this argument here, or this equation here, tells us just step by step, right? Take a partial with respect to position, take a partial with respect to velocity of this Lagrangian, and then that will end up giving us an equation of motion. The partial with respect to the position is equal to minus kx, and the partial with respect to the velocity is mx dot. Now notice that this minus kx term, that is the force that we've seen before, the spring force. So before proceeding, I just want to say a few words about this. Here we have the spring force, and notice that that came about as the derivative of the Lagrangian with respect to x. And if we play that out, we have the following. In this problem, notice the kinetic energy term does not depend on x. So in this problem, we have the partial with respect to x of kinetic energy is 0, and we end up with minus du dx, a gradient of the potential in the x direction. That ends up being playing the role of the spring force. And what we're going to see is, if a force is conservative, you can write down a potential associated with a force, and the gradient of that potential with a minus sign is equal to that force. So this is going to come up over and over, but this partial of the Lagrangian with respect to the position coordinate is the force, because it's the gradient of the associated potential. Okay. The final piece that we need here is the time derivative of that second term, the derivative of the Lagrangian with respect to velocity, which is d dt of mx dot. Mass is constant, so that comes outside. And another derivative of x dot gives us x double dot. So now our equation of motion is going to come out of this expression. So on the left-hand side, we found x double dot times m, and on the right-hand side, we have minus kx, and once again, we arrive at the equation of motion, like so. So remember, in mechanics, one of the main goals is to come up with an equation of motion of a given system, and it looks like we can do that. Well, first we did that using Newton's second law up here, but then we just turned to a quantity that depends only on energy, and we were able to get into the same place. Okay, so somehow energy has this power in mechanics. There's a quantity, if we track the energy of the system, we can access the final equation of motion in much the same way as we did using forces and vectors and momentum principle and Newton's second law. And it's the case that in kind of modern theoretical physics, using the Lagrangian approach or similar approaches, whether you're doing general relativity or string theory or even biophysics, it's based on energy arguments. And so we're going to dive much deeper into this topic of energy in this course. Okay, so now let's have a careful definition of kinetic energy and this quantity that we're going to call work, which can change the energy of a system. And we're going to start with humble beginnings, where we have a single point particle of mass m moving with a velocity v. Okay. And we want to understand, how does the kinetic energy change in time? In other words, can we come up with an expression dt dt, d capital T, d lowercase t? And, an example of this is kind of the canonical question, like the following. You have some track, and on it you have an object, of mass m with an initial velocity of 0. And that object starts some height h up off the ground. When the object gets to the bottom of the track, what is the final speed of this object? Right? In other words, we know the initial speed and the initial kinetic energy. What is the final energy? And let's say there's no friction. Okay, so given the initial kinetic energy and given that we want the final kinetic energy, how do we go about finding that? How do we find delta T, the final minus initial kinetic energy? So let's see how this is going to play out then. We start with this definition of kinetic energy, 1/2 mv squared, and we think about this v squared term as the dot product of the velocity with itself. We then construct the time derivative of this kinetic energy, m over 2 d dt of v squared, which is v dot with itself. And here we assume the mass is constant. Okay, so that it has come outside of the time derivative. Well, the time derivative of the dot product, as you've already shown and proved, in fact, gives us two terms via the product rule. But those two terms are the same. And they're the same because for the dot product, the order doesn't matter. So we have two of these terms, dv dt dot v, and these twos cancel with the 1/2. And we also notice that, as an aside over here, we can say dv dt times m is d dt of mv, assuming that mass is constant, which we've already assumed, which is dp dt, the rate of change of the momentum. Okay, so we express this as dp dt dotted with v. Okay, so everything so far is basically mathy. Now we want to do some physics interpretation of this, right? So over here we say by Newton's second law, we know what dp dt is. That's the net force on the system. So we can use that on the right-hand side and say my net force of my system dotted into the velocity of my system tells me about the rate of change of the kinetic energy. Okay. Again, on the physics side, we know that the velocity is the rate of change of the position vector. So if we look at very brief time intervals dt, we find that the change in kinetic energy over that very brief time interval is given by F net dotted with dr. So v is dr dt, so that dr is on this right-hand side, and on the left-hand side we have d capital T, a little change of kinetic energy. Okay. So remember our goal was, if we know the initial kinetic energy, we want the final kinetic energy, and we can think about delta T as the final minus the initial kinetic energy. Okay, and in the limit of very small time steps, we have we know what the incremental change in kinetic energy is, and so if we want the change in kinetic energy over a macroscopic time, this capital delta T, then we're going to want to integrate our expression for the change in kinetic energy. So our next step is to integrate this expression. And when we do that, we have the following. Like so. We're going to integrate this from the initial position of the object to the final one, and the initial kinetic energy to the final. So on the left-hand side, we just have kinetic energy evaluated at the limits. And on the right-hand side, we keep that integral as is. On the left-hand side, again, that's a capital delta t, and on the right-hand side, we keep that integral as is. Okay. And this is our so-called work kinetic energy theorem. Which says that in order to change the kinetic energy of this point particle, you must apply a force over a displacement such that the dot product of those two is non-zero, and you add up all of those units of work, or those incremental pieces of work, over the full path from the initial to final position. That's what this integral is telling us. And this right-hand side goes by a name that you're all familiar with called work. And that work is simply defined as the integral on the right-hand side. Okay. So some caveats here is, so far we applied this to a single particle. Okay. And a single particle cannot deform. So when you have a system that can deform, like the shape of the object can change, then you can do work, but that doesn't necessarily change the kinetic energy of the system. So be very careful about systems that deform. And we'll talk about those more in the future. In other words, in general, the work does not go 100% into kinetic energy. So when you do work on a system, that doesn't necessarily mean all of that work goes into kinetic energy. In this derivation, it does, but we're talking about a single point particle that cannot be deformed. Okay. What we're going to see and use in the future is the so-called energy principle. And the energy principle is the following: that in order to change the energy of the system, not just the kinetic energy, but the energy of the system, you can do work, or you can have other energy transfers. Okay. And we have to think about, in the future, we'll think about what are some of these other energy transfers, but just as a preview, think about when you cook toast. You put bread into a toaster, you turn on the toaster, the coils heat up, the energy of that toaster is increasing, not because you're applying a force acting over a distance, no, but rather you're dissipating energy, electrical energy, and creating thermal or heat energy. So you've changed the system energy not by doing work, but rather by transferring energy into the system electrically. So there's other ways to increase the energy of the system, not just by doing work. So now that we've seen the work kinetic energy theorem, let's see how to actually use it, how to apply it, how to actually use it in practice. And let's return to our original question. We have a mass and some track, and we want to know, given the speed at the start, how do we find the speed at the end? Okay. And that's a question of what is the change in kinetic energy of this system, the system being the box in this case. And so let's look at the applied forces that are acting on the box, dotted into the displacement vector for each little time interval, integrate that all up, and that'll tell us the change in kinetic energy, and we should be done. So this is an exercise in computing the right-hand side here of the work kinetic energy theorem, and you'll notice that it's an integral, fine, but it's the integral of a dot product, right? So we just have to make sure that we understand how to do the integral of this dot product, and we'll work in this example first. So what the right-hand side tells us is we need to know what the forces are on this object. So let's draw some of those forces, okay? At any given time, the mass is going to experience a force of gravity. Okay, I'll call that F sub g, and if we give ourselves a coordinate system, I'll say y increases up, the y hat direction is up, the x hat direction is to the right. So the force of gravity is always going to point in the y direction, and specifically, it will always point in the minus y direction. We are going to also have a normal force, Fn, or sometimes just n, and in general, we're going to have two components to that normal force, okay? We're going to have a normal force that in general will point perpendicular to the track. So that normal force will have components in both the x and the y direction. Okay. What are the components? Well, we don't yet know, but there's going to be both x and y components. Okay. So when we compute the total work, there's going to be, in general, work done by each force separately. So we have work by gravity, and we have work by the normal force, and we can call this Wg, and we can call the second one Wn, and so the total work on the system is equal to the gravitational and normal force works added together. Okay. Notice that's different. That's different than saying the work is equal to the net force integrated, where here we're looking at the work from each force separately, and then we add up those contributions to get the total work. All right. The first thing we're going to see is that the work done by the normal force is 0. Okay. How do we see that? The work done by the normal force is equal to the integral of the normal force dotted into the displacement vector dr. And that integral is going to be 0 because this dot product is going to be 0. How do we know the dot product is going to be 0? Well, if we notice that the normal force is always perpendicular to the track, but the displacement vector dr at any given instant is going to be tangent to the track. Okay. So this dot product will give us, by the dot product, we know that we can write the dot product as the magnitude of the normal force times the magnitude of dr times cosine theta. But here theta is going to be 90 degrees, so that cosine of theta is 0. So the work done by the normal force is the integral of 0, which is just going to give us 0. So we have no work done by the normal force, and that's going to be generally true. The normal force does no work. Okay, next we have the gravitational force. Now that one we're going to actually have to calculate out. All right. And recall we have an expression for Fg. And the key idea is that Fg has no x component, only has a y component. If we think about the dr piece, in general, that has a displacement in the x and in the y direction, but when you dot that into Fg, you get 0 times dx plus minus mg times dy, and so that dot product gives you minus mg dy. So when we integrate this work integral, we end up with the integral of minus mg dy from the starting y-coordinate, which we said was height h off the ground, to the ending y-coordinate, which let's say is 0 when we get to the ground. So this integral is minus mg times y evaluated at the limits, h and 0. So that would be minus mg times y of 0 minus y equals h, which gives you a total work of plus mgh. So the work done by gravity is positive and equal to mgh. Notice that that's also the same expression for the stored potential energy, but here our whole system was only the particle, right? So just to rehash, our system was just this block, not including the Earth. And so the force of gravity in that case was an external force, and that external force did work, and the amount of work was equal to mgh. So now we can use the work kinetic energy theorem, again back on the left side here, and we see that there's no work done by the normal force, but we do have work done by gravity, and that work by the work kinetic energy theorem gives us our change in kinetic energy. So T final minus T initial is equal to mgh. We said in this problem that the box started at rest, so T final is mgh. T final is the kinetic energy, so we can find the final speed. And notice our final speed will not depend on the mass of the box, but it will depend on how high up the box started. Okay? So I just wanted us to have a brief example here to see how we go from an expression of an integral of a dot product of a force and a displacement. How do we actually play that out into an integral that we can actually evaluate with specific limits? And in particular, in general, this dr could point in more than one direction. It could have an x and a y component. In this problem, only the y component mattered because there's no horizontal component to the force. In general, we're going to have forces that have components in both directions, and we'll need to see how to express this dot product more generally. And we'll practice that going forward as well. But until next time, take care and be well.